Okay, let's get started with the second and last talk this afternoon. So our speaker is Slofstra from University of Waterloo, and his title is Positivity is Undecidable in Product Algebras.
Thanks.
Okay.
Yeah, okay.
Got it.
So this is joint work with Arthur Mehta and Yuming Zhao. So the basic question I want to look at is a really simple one. So let's say we have a C-star algebra, and have in mind something concrete, like maybe the C-star algebra of product of free groups, okay? And all I want to ask is, like, if you've got an element of this algebra, when is A positive? And of course, that's answered in the following way. That's if and only if A equals B star B for some B in A, or if and only if there's a representation there is not a representation, isn't a representation, say phi A to B of H with the inner product of V phi A V less than 0. Okay, that's the standard definition of, you could take either of these to be a definition of positive if you wanted to. And it's kind of interesting to look at this, just as a theme for the rest of the talk, that the first one is what you would want to do if you want to show something is positive. You would try and find B. And the second one is what you would want to do if you want to show that A isn't positive, try and find a representation where it's negative. But of course, in a C-star algebra, this is kind of more of maybe an abstract idea of what you might do, but we might not have a concrete handle on what A is really to do this, or even if we do, we might not have a concrete handle on how to address elements of the C-star algebra. So for the first thing, let's change the setting a little bit.
Very quickly,
yeah.
Objection. So you want to say less than 0 or not greater than 0, because we have complex numbers.
Yeah, I'm going to say positive. Oh, and yeah, I was wondering if anybody would call me on that. In my notes, it says SA here. Yeah. Yeah. So, yeah. But then I skipped that. Yeah. Yeah. And I'm probably going to skip it later on in the talk too. Just assume that things are self-adjoint. Yeah. Okay, so what I want to do is change the setting, first of all, just to make this a more concrete problem. But really, this is what I have in mind, is some C-star algebra like this. Okay, so let's actually change A to be like an Archimedean star algebra, let's say. I might define Archimedean at some point if you haven't seen it, but basically this is a condition to guarantee that we actually have a state. Okay, so we're not just talking about a totally abstract C-star algebra. And so now maybe I have in mind like the group algebra of Fn cross Fn. Okay, and now in a star algebra I need to say what positive actually means. So if we're going to go after something that relates to C-star algebras, let's say that A is positive. If phi A is positive for all star representations, phi A to B of H. Okay. And then, let's see. So,
Archimedean just means that there exists state.
Archimedean actually means, I can say what it means, it's not hard. It means that if you have, for any, let's say, self-adjoint element, there exists lambda. So for all A, there exists lambda such that lambda minus A star A is sum of squares, Hermitian sum of squares. It's like a boundedness condition. So make sure you actually can talk about norms of things. Yeah.
Inside the star.
Yeah, and we're going to talk a lot about this condition later, so that's why I didn't want to define it right now. Yeah, all algebras will be unidal as well. Yeah. Okay, so what I want to look at is the condition, or sorry, the decision problem, not the condition. So given A in A, when is A positive in this sense? And I want to think of that as kind of an algorithmic question. So before kind of getting into the content of the talk, I kind of like just to say, looking at this, okay, what kind of answers can we expect of this? What are we actually looking for here? Because I know not everybody in operator algebras, it's not necessarily the type of question you normally think about. So what kind of answer could we look for here? So the thing we might be looking for first is just to know whether this question is decidable. Okay, so we would say this is decidable. I'm not going to bother with formal definitions, but let me say what that would mean. There is a computer program which halts on all inputs A and returns true if A positive and false otherwise. Okay. So the first thing looking at this is you need to be able to feed your thing into a computer program. So looking at that, the question doesn't make sense because these are complex star algebras, and you can't put a general complex number into a computer program, right? So instead, we need to change the question a little bit. So we need to pick. So I'm going to just say, given A in A, it just saves a lot of time to say that. But really, what we mean is to say something like pick some generating set X, and then maybe we actually have some concrete representation, generating set big X, excuse me, and then represent, or maybe we just look at elements A, which are non-commutative star polynomials over the generating set X. Okay, so what we say instead here, this is code for given some polynomial with rational coefficients, which we can put into a computer, right? Then we look at the image inside the algebra that we're interested in and ask whether it's positive there. So, for a concrete example here, we're really looking at things maybe from Q Fn cross Fn, or Q Fn, or whatever algebra that we're looking at, and asking about positivity of those. Yeah, so you mean for A? Yeah, right. So this question is pretty interesting from a computational standpoint if A has a really bad presentation. But I want to look at ones where we have like a finite presentation. So, well, I don't think you will be able to compute the norm. So yeah, in terms of like a computable presentation as a C-star algebra, no. Yeah, but I'm not going to worry about that question. I'm just going to worry about the positivity question. Yeah.
I guess just complex rationals. Even though you look at fluff adjoints, sometimes you have to use complex rational polynomial.
You mean like QI or yeah? So right, you could replace this with any computable field. Turns out that what I'm going to do is we'll work with just rational coefficients. But
yeah. My point is that I think you're missing some of the self-adjoints from algebra, but you just don't look at.
Oh yeah, no, you're not going to get all the self-adjoints from this.
Not even
yeah.
that set. That's what we meant.
Depends on the algebra, but that's like.
Yeah. The dense set, but we just look at the
well, it depends on what the generating set you picked is. You could add I in there, for instance. Right. So, yeah. Yeah.
And since we're getting picked, why do you care about the denominators? Why don't you just clear the denominators? Because you're just looking for positivity.
Yeah, you could just do Z. Yeah, that would be fine too. Yeah. Now, if you were programming this, you'd much prefer to have to program integers. Yeah, so that would be the first thing you'd ask as a programmer given this as the assignment. Yeah. Yeah. Okay. let's say you did know this was decidable, so you had a computer program to do it, right? Then you would start to look at like efficient presentations. So probably people know about this. Like this is not putting any constraint on how much, time it has to halt, but we don't say how long it has to take to halt. It doesn't put any constraint on computer memory or anything like that. So if you once you know something's decidable, you can start saying, is this something we could actually run on a real computer? But you can also go the other way here and actually make this. You could say, well, maybe if it's not decidable, we can ask for something less. Okay, so for instance, there's a class RE. Okay, so here we would be asking there is a computer program which if A is positive, halts and returns true. Okay, and doesn't halt if A is not positive. So this doesn't really give you practical, practical way of solving the problem, because you might be running this thing and it's just running for a long time, and if it doesn't halt, you just don't know if it's going to run forever because alpha is not positive, or if it just hasn't halted yet and it is positive. So this is very closely related to whether you can prove that it halts, right? It's basically asking whether there's the existence of a proof that your certificate that your thing halts. We also have decidable is inside co-RE, which is the complement of this thing. It's the things where it halts if A is not positive, okay, but doesn't have to halt on the positive things, or doesn't halt on the positive things. It's also good to see an example, by the way, of something that's in RE. So the halting problem is an example of something that's in RE. And this is the set of Turing machines or computer programs which do halt, let's say, on empty input. Okay, and you can see that that has the same character as this question. If you're given a computer program and you want to know if it halts, just run it. If it halts, right? And if it doesn't halt, you don't know anything. You don't know if it just hasn't halted yet or if it's about to halt. And it's important to know if you haven't seen this before, this is a complete problem for this class. So if you can show something is at least as hard as the halting problem, okay, then you know that basically you contain this whole class of RE problems. And co-RE has also a complete problem, co-halt, the Turing machines that don't halt. Where you can, these are the things where you can kind of prove the negative. And finally, both of these, I was going to move this over more so that I would have one more column here, but maybe I'll just fit it in over here. RE and co-RE are both contained in a larger class, well, more than one, but I'm going to highlight pi02 here. Okay, so this is the sentences of the form like for all epsilon, or for, sorry, not for all epsilon, for all there exists. Which is like RE is there exists computation that halts, and this is for all computational paths none halt. Okay, and this is like for all inputs there exists a computation path that halts. That's pi02. So this is a larger, more difficult problems in there. Okay, so that's the type of answer we would be looking for this problem. How difficult is it? Is it something that's over on this side or on this side? Okay, so back to actual algebra. So let's say A is sum of squares. If A is a sum of permission squares, okay, and let's say A is, I'm not sure what the best term for this is. I kind of picked this at random when writing my notes here. Let's say it's finite dimensionally positive if phi A is positive for all finite dimensional star representations. Okay. So, and what we have is that if something is sum of squares, then it's positive, clearly. And if something's positive, then it's finite dimensionally positive. Okay. And this first condition is good for showing that something is positive if you can find that it's a sum of squares. that will prove that it is positive. And this one is good for showing something's not positive, right? If you can find something where this isn't true, and by the way, why are we picking finite dimensional? Well, here we would try to find some representation. It's pretty hard to work with the infinite dimensional ones if you're just dealing with, like, let's say, star polynomials over some unitaries here or whatever. But a finite dimensional representation is, really easy to work with. So if you can find a finite dimensional representation, you have a concrete demonstration that something, if you can find a finite dimensional representation where it's not positive, then you know your element isn't positive. That's a way to prove that. Okay, so let's make a definition. Let's say A is Archimedean closed if every positive element has a sum of squares decomposition, so S and S if and only if positive. Okay, and this should be a familiar term. A is RFD if positive if and only if finite dimensionally positive. Okay. And then Archimedean closed, so our condition 1 here, says that if something is positive, then we can always prove, right? So 1 can always prove that a positive element is positive with a sum of squares decomposition. Okay, in other words, we're saying that the positive, this positive problem here is contained in RE. Okay, and condition 2 is saying that we can always prove that something's not positive by finding a specific finite dimensional representation. Okay, and so that's saying that our problem is contained in co-RE. Okay, and then if you have 1 and 2, then you're in RE and co-RE, right? And it turns out that's I should element here really. Which is just a set of decidable problems, right? So if we know that 1 and 2 both hold, we have a procedure for deciding positivity. What do? We look through sum of squares decompositions for proof that it's positive, and at the same time we look through finite dimensional representations for a proof that it's negative. And if 1 and 2 both hold, then one of those is eventually going to terminate, and then we'll know which one it is. So, okay. So our question then is, when do 1 and 2 hold? That would answer our, that would tell us that for that algebra we could answer our positivity question. Yeah. So okay, so I should just mention, I'd be remiss if I didn't, that in the commutative case, this is a problem with a really long history. Okay. The RFD problem is not so interesting, but the sum of squares problem, the Archimedean closed problem, is a problem of if you have a positive function, when is it expressible as a sum of squares? And when you find that it isn't, you can start asking for things like rational sums of squares and so on. There's lots of theorems of positive Stellensatz and non-negative Stellensatz and so on. Okay. In particular, in here you'll find that I think this group algebra is not Archimedean closed. Okay. But we're interested in the non-commutative case. So time to start erasing, I guess. Okay, so the first thing we find in the non-commutative case is that there are a bunch of examples where 1 and 2 do hold. Okay, in particular, if you look at the group algebra of the free group. Okay, I've seen this attributed to Smutkin and well, Smutkin and Choi, I think, for the RFD part. And then we can also do here algebras, I think, like Z2 to the star n. And also, these are Archimedean, but here, even a non-Archimedean case, just star polynomials in arbitrary variables is the well-known result of Helton. You have 1 and 2 both. And in fact, in these cases, the fact that these holes are linked, and actually, in terms of having an algorithm to decide our positivity question, just erased, I guess, you know degree bounds as well for sums of squares. If something is positive, it has a sum of squares up to, guaranteed of a certain degree. And you also know dimension bounds on how high a dimension you have to pick. So you can use those for algorithms to decide positivity. So if we know these are positive, then we might say, well, let's look at the next most difficult case. Before I say that, though, let me go to the general case, because there is something we can say in the general case, okay? And that's this. I've also seen this attributed to Smutkin. Positive Selensatz. And it says that this is specifically for the Archimedean case. A is positive if and only if A plus epsilon is a sum of squares for all epsilon greater than 0. This is a really cool result. But interestingly enough, it doesn't put our positivity problem in either RE or co-RE. So you have to think about why. So imagine we want to prove that, well, okay, so it's clear why we can't use it to prove positivity, because we have to prove something for all epsilon, right? That's not going to be so easy to do, but maybe we could try and prove it for, we could try and use it to show something isn't positive. So if we can find an epsilon such that A plus epsilon is not a sum of squares, we know our thing isn't positive. But in general, this theorem doesn't give us any degree bounds on how high degree our BIs have to be there. So we would be searching through all possible, you want it to be K, and there's no bound on K either, by the way, so we don't know how many elements we're going to have to pick in our decomposition. So we're searching. If we don't find one, we don't know if it's not sum of squares, or we just haven't found it yet. What it does tell us is that this problem is contained in pi 0,2, right? It's for all epsilon, there exists something. That's a pi 0,2 problem. So it does put an upper bound on this thing, but not a particularly nice upper bound. But, they're like linear in the degree of the polynomial you start with. Yeah. Yeah, so I said, if we don't know the general case, we should look at what the next easiest case is, and arguably that would be product of free groups. So something like Fn cross Fn, or we could do for other algebras that appear up there, the products of those algebras as well. There's our, since tensor product is in the title, I better write that this is a tensor product at least once. Anyway. Oop. Okay. So you probably know, though, we're going to ask whether 1 or 2 hold for this. You probably know that this algebra is RFD. So RFD, if and only if Kahn embedding is true, which is contradicted by MIP star equals RE. So these algebras are not, the products of these algebras are not RFD. Yeah. Let me explain a little bit about how that works in this setting. I think we've seen correlations, norms, right? That computing norms is uncomputable. Was it a question?
Just a quick question of clarification.
Mm-hmm.
The reverse directions from positives are in fact to condition
Positive.
Condition one implies positives are the converse of that.
Oh, right. So not necessarily like that. Good in the commutative case. There are situations where the problem is decidable, but you can only find rational sums of squares. So it's the question about whether it's an RE is just whether there is some proof system, not sums of squares specifically.
If there was some reason why this one was special, or if it was just a sufficient condition.
Yeah, historical reasons. Yeah, but also, I mean, would you be happy if somebody just said, "Hey, I can prove this thing is positive," a really abstract proof? I have a way of doing it, but it doesn't. Sum of squares is nice. It gives you a certificate that we all understand. And if the method of proof also has that feature, then you're fine. If not, maybe you wouldn't be so happy with it. Yeah. Okay, so I wanted to say something about MIP star equals RE from this point of view. Okay, so what does it say? And of course, a theorem of Anand Natarajan and Denfeng Ji and Thomas Vidic, John Wright, and Henry. So there is a mapping. So this is going to go from Turing machines, okay? But if you don't like that, you can just think computer programs in some chosen computer language to elements of Q, Z star N, M, Z star N, M. And I wasn't sure if I'm allowed to put Q here or not. I think I can just round if it's not in Q, but decided to go out on a limb and just put Q there. It might have to be a larger field, but no, I'm convinced by my rounding argument now that I said it out loud. So Q is fine there, I think. Okay. And I should say here, N and M depend on M, so this is not uniform in N and M here. So such that one, if M halts, then there is a finite dimensional representation phi. Let's say from our algebra here to MNC and V in Cn with, so we got alpha M, and we're going to apply phi to it. And then on V, this isn't just negative, but actually equal to, say, -1/2. And then if M doesn't halt, then not only is our alpha of M positive, well, I should say phi alpha of M is greater than or equal to, let's say, 1/2 identity for all finite dimensional representations. Phi. So in other words, this minus 1/2 is FD positive. Okay. What does it mean for our problem? Well, it doesn't directly relate to our problem of positivity, but it does relate to some other problems. So let's write down some other problems. We could look at the problem of finite positivity, right? Is and A FD positive. Okay, or we could look at, it seems like this problem, and this is very important, it's actually about a stronger problem, gapped positivity, okay, which is, so this problem is to decide whether A is greater than a half or there exists phi v finite dimensional. Oh, actually, gap positivity, let's not put this in yet. Or there exists phi v with v phi a v equal to minus a half. Promise that one of the two is the case. Okay. In this type of promise problem, it's the same as these other types of problems. You have to figure this out on the given input, but you don't have to do anything when the promise doesn't hold. There's no, you don't get judged on that. You only get judged on the inputs where the promise holds. And then finally, I can put these both together and look at the gapped finite positivity, which is same as here. But now here, I look at only finite dimensional. Okay, so 3 new problems to look at here. And then if we write out what the consequence is from ipstar equals RE, okay, we have, so this says that the gapped finite positivity problem is at least as hard as solving the halting problem, okay? And then if you look at the problem, you can also see that it's contained inside of RE, because what can you do? You can, you have to decide whether you're, oh, I didn't put enough finite dimensional in decide whether, not whether A is greater than or equal to half, but A minus a half is FD positive. Yeah, okay, there we go. So what can we do? We can, oh, excuse me. I said that this contains RE, but that's backwards, right? So it contains co-RE, right? So because here, the halting case is when we're not positive. Yeah. So this is saying we have a mapping from Turing machines to alpha m's. And now you imagine if you could solve this gapped finite positivity problem, you would be able to tell if the Turing machine halts or not, right? And how does it, the case where the Turing machine, sorry, the case when alpha m is positive is the case when the Turing machine doesn't halt, okay? And you can show that it's in co-RE by searching through finite dimensional representations until you find one where it's negative. And finite positivity is also contained in co-RE. So I think what you get from that is this. Both of these end up being equal to co-RE. Okay. On the other hand, if we think about this Smitkin-Posistellensatz, it wasn't very good for our problem of positivity, but for gapped positivity, it works a lot better. Okay. Imagine that A is greater than or equal to a half. That means A minus a half is positive. So is it still on the board? It is. Okay. So if A minus a half is positive, then A minus a half plus a half is a sum of squares. So if you are in the positive case of gapped positivity, that's the point of being greater than a half here. That means you have to have a sum of squares decomposition. So so gapped positivity is contained inside of RE. Okay. Yeah.
Is your
Oh, yeah, yes, good point. Yeah, right, it's not required to be a unit vector. You can just, yeah, it is a unit vector. Yeah, yeah. Yeah. No, thank you for pointing that out. Yeah, I don't have the out of that one being in my notes and I missed it. I just forgot to say it. Where else did I put? Down here, yeah, that's really important. Yeah. It doesn't directly map on, I don't think. Yeah. Yeah, if you plug in a game functional for the alpha m, but I'm not sure that the finite positivity is not the same as exact finite dimensional perfect strategy. Yeah, this is just a different problem. Yeah. Oh wait, it is. It's is a value greater than a half, greater than, strictly greater than a half. Yep.
So you're assuming that A is positive, right? Because otherwise, of course, you can't hope this to be exactly minus 1 half. I mean, if A is negative already.
Oh, yeah, that's also a good point. Should I say, yeah, okay, that's a good point because let's say we scale A, right? So here, I really should pick less than or equal to. Yeah, yeah, yeah. Yeah, once I put the unit vector, yeah. Less than or equal to minus a half. Yeah, right, okay, I could either do that or I can put this to be in the unit disk rather than, yeah, less than or equal to 1 for the norm, yeah. Okay, hopefully that's all fixed. Okay. Okay, what were we saying? This is in RE. And then if you think about what, if our algebra was RFD, that would imply that co-RE is, so RFD, we said, means that our, let's see, what would happen if we had RFD? We would have these two being the same. Okay, so our this problem and this problem are the same, and therefore we would have co-RE contained inside of RE. Which of course can't happen. Okay, so that's how we, from this point of view, how we know that this algebra or the complex version of that is not RFD. Okay, so our goal in the project we're working on with Arthur and Yuming, we have these two closely connected properties that are related to this positivity question, and we have examples where they're the same. Here we have something which is now, we know, not RFD. So is it also true that it's not Archimedean closed? And it's a basic question, are there positive things that are not sum of squares? Potentially a much easier question than asking about whether it's RFD, but surprisingly wasn't known. So you could look for things that you can prove are positive in some other way, and that's usually how these things work when you show something's not a sum of squares. You try and show something is positive in some other way, and then but show that it doesn't have a sum of squares nonetheless. But if we take inspiration from this proof, we can prove something's not RFD with computational argument. We should try and do the same thing for Archimedean closed. That was our thinking. So here's the theorem. Maybe we'll fit it over here. So for large enough n, there's a mapping from Turing machines M to alpha of M in this algebra here. Such that M does not halt. So this isn't about the gaps problem, so we don't have to write out two cases. We can just say M does not halt if and only if alpha M is positive. Okay, so conclusion out of that then is that this problem of deciding positivity contains co-RE, okay? And that implies that this algebra is not Archimedean closed. Because if it was, we'd have a way of putting this inside of RE. We'd be able to prove when things are positive if every positive element had a sum of squares. But we can't have co-RE inside of RE, so not possible. So it's kind of a roundabout way of showing that there are things that are positive but not sums of squares. We can also show, let's say A is trace positive if tau A is greater than or equal to 0 for all tracial states. Oh, I gotta move this up now, don't I? Okay, and we can show that, again, for large enough n, there is a mapping, all the same stuff, except here now the algebra changes to the free group, okay, so rather than a product, just the ordinary free group. And the result is, such that M does not halt if and only if alpha M is trace positive. Okay. Yeah. And again, this gives us, so here actually it was known that there are things which are, so you can ask to be, there's a way of showing that things are trace positive by exhibiting them as sums of squares plus commutators. Okay? And it was known that there were things that are trace positive, but not sums of squares plus commutators for this algebra. The proof used the usual type of method you use for these things. You find some element which you can show as a rational sum of squares plus commutators, and that proves positivity. But then you show in a different method that it's not a sum of squares, actually by reduction to the commutative case. So the interesting thing about this is it also shows there are elements that aren't rational sums of squares, or any kind of method you would have for proving positivity. For any kind of method you have for proving positivity, there's always some element which is positive but doesn't have that certificate. And the other thing, both of these theorems also work with Fn replaced by one of these algebras, either CFn replaced by that, or we can also do the unbounded case. So just arbitrary star polynomials. Okay, so in the trace theorem here, you just have one copy, and in the version up here, you take products of these algebras with themselves. Yeah. Okay. The construction is completely explicit, but you know, you have to use like the usual type of diagonalization argument to get things that are positive but not sums of squares out of it. Yeah. Yeah, like use a fixed point theorem to get an explicit, but the encoding is explicit. So yeah. I want to mention one more thing related to this for context, and then we'll see if there's time for the proof or not. Maybe you might be out of luck, but let's see. Right, I wanted to say, what about gapped positivity? This doesn't say anything about gapped positivity, and in fact, we take advantage of that. It's easier to prove it's easier to prove a statement like this when you're not having to deal with gapped positivity, because if you think about, you want when the Turing machine halts, you want your thing to be not positive, so it needs to have a negative eigenvalue, but you can make that negative eigenvalue really small if you want. In particular, you could make it like 1 over the running time of the Turing machine. So when you can do an argument like that, that makes it a lot easier than trying to do gapped arguments. Okay, but what about the gapped one? Let's see. So there's another conjecture that's related to MIP star equals RE, which is MIP co equals co RE. Okay, it's a conjecture, but I think there's a reasonable chance that it's true. And this would imply that gapped positivity, we said this one was inside of RE. But so this conjecture is that this is equal to RE. And it's kind of interesting to compare. So that would imply, positivity is the way around this. Yeah, this way. Okay, so that would imply that the positivity contains both RE and co-RE. And we know, remember, the upper bound on that was pi 0, 2. So I think it's natural to conjecture off of that. And we don't know how to prove this, that positivity is equal to pi 0, 2. So even assuming this conjecture, you mean? Yeah, no, we don't know how to. Well, yeah, okay, yeah, if this is true in a nice enough form, then probably, yeah, actually. I'm not sure. Yeah, I have to think about that a little bit. Depends on, for some value of nice, that's true, but if this is true in a nice way, but I'm not sure how nice it, I have to think about how nice that would have to be.
So, William, when the conjecture here, you think positivity for any algebra, or is it for?
Yeah, thank you. Yeah, right, for this algebra specifically, and the related algebras up there. Yep. Which I guess would mean, so this is the upper bound for any algebra. So it's basically saying that this is tight for algebras in general. And then you get into questions like, what are the possibilities? Can there be algebras which are intermediate to this undecidable, and so on? But I don't know any reasonable conjectures for that. Okay. Oh yeah, one other thing, because the gap, so you could ask whether you would get the same, if you could prove this, would it prove that your algebra is not Archimedean closed? And it wouldn't, right? Because this is compatible with being Archimedean closed. If positivity was equal to RE, right, that would mean that everything has a sum of squares proof. That would be fine. So although this is a lot easier than proving a gapped version, this is you can't rely on that to prove something like non-Archimedean closed. Okay. I should make some general remark about the proof. Maybe we'll end in a minute, but if you want to hear more about the proof, I'm happy to say. Is there anything I want to say about the proof in 1 minute? Pardon?
The usual stopping time is 4:30, I think.
Oh, I thought we stop at 10 before the stopping time for questions. Well, I was enjoying when people stopped.
Okay, well,
When so, yeah, I will stop here, and then if you want to know about the proof, you can ask.